Hello and welcome. When I first practiced data structures and algorithms for coding interviews, there's one type of question that I always struggle with, and whenever I see such a problem, I always feel nervous and want to run away. It messed me up in many coding interviews, and I could not figure out how to solve it properly. You guess it, it's dynamic programming. Dynamic programming is hard, but it's a very common type of question asked in a real coding interview. In this video, I'll explain the core idea of dynamic programming, as well as how I identify and solve such a problem. I will use a LeetCode question as an example. I believe this video will help you build more intuition around DB problems, and this will give you more confidence to solve these questions in a real coding interview. So without further ado, let's dive in. The question we will go over today is called longest common subsequence. So this is a very standard DB problem. So let's get into the questions. Alright, so we are given two strings, text1 and text2, and we want to return the length of the longest common subsequence. And if there is no common subsequence, we're going to return 0. And a subsequence of a string is a new string generated from the original string with some characters cannot be none, deleted without changing the relative order of the remaining characters. So for example, we see that ACE is a subsequence of A, B, C, D, E. So we get A, C, and E, right? So these characters doesn't need to be adjacent, but they need to follow the same order in the original string. And a common subsequence of two strings is a subsequence that is common to both strings. So they also provided two examples here. So the first example is this. So we have the first string A, B, C, D, E, and the second string is ACE. So we can clearly see that ACE is the longest common subsequence, right? And it has a size of 3, so we're going to return 3. For the second example, the first string is ABC. The second string is also ABC. So that means the longest common subsequence is ABC, and the size of it is 3. So how would I approach this problem? Whenever I see a DB problem, the first thing I always do is start with a brute force solution. Our brute force solution would be we try all possible combination of subsequence and we try to find the longest one. So in order to do that, we're going to start at the beginning of both strings. So the first value in the tuple is going to be I, which represents the index of the first string. And the second value in the tuple is J, which represents the index of the second string. We see that at index 0, the character at I and J match each other, right? The only option we have is to move both index to the next position. So we're going to move to 1, 1. So now at index 1, we see that B is not equal to C. And because B is not equal to C, that means we cannot use this character in the subsequence. So we have two options here. We can either increment I or we can increment J. So if we increment I, we're going to move to 2, 1. And if we increment J, we're going to move to 1, 2. So we see that there are two different directions here. And the direction that gives us the longest common subsequence is going to be the direction that we choose. So at 2, 1, so 2 is C, 1 is C, so there's a match. So whenever there is a match, it makes sense to move both pointers forward. So we're going to move I to 3, J to 2. So now at 3, 2, 3 is D, 2 is E. So there's a mismatch. So we have two options. We can move I forward or we can move J forward. So I now is at E and J is also at E. So 4 is E. 2 is also E, so we're going to move to 5, 3. And when we reach 5, 3, we see that 5 is the end of the first string, 3 is the end of the second string, right? Whenever we reach the end of both strings, we know that we already found the subsequence. And what is the size of the subsequence? 1, 2, and then 3. When we reach this problem, this one gives us a subsequence of size 3. How about this direction? So 3, 3. So 3 here is going to be D. 3 here is going to be the end of the string, the end of text 2. So whenever we reach the end of text 2, we know that we cannot continue, right? And what is the size of the subsequence if we follow this path? It's going to be 2. Alright, so the first matching character is A and the second matching character is C. So the size of that subsequence is 2. So we continue this side of the subproblem. So 1 is B. The character at index 1 for text 1 is B. 2 is E. So B doesn't match E. That means we also have two options. We can either move I forward, we move to 2, 2, or we can move J forward. So we're going to move to 1, 3. So let's start with 1, 3 first. So 1 is character B, right, of the first string, and 3 is the last character of the second string. So whenever we reach the end of the second string, that means we know we cannot continue, right? We cannot continue the matching. We need to return the longest common subsequence of this path, and the answer here is going to be 1, right? We only have one matching character here, which is A. And the same thing for 2, 2. So 2 for the first string is going to be a C. 2 for the second string is going to be an E. So we have two options. We're going to go to 3, 2. Or we can go to 2, 3. So let's take 2, 3 for example. So 2 for the first string is C, 3 for the second string is the last character. So whenever we see this, we're going to return 1. How about 3, 2? So 3 of the first string is a D, 2 for the second string is an E. So we have two options. We can move to 4, 2. So 3 of the first string is a D, 3 for the second string is empty string. We have to stop here. And the number of matching character in this case is only 1. Right, we only have one matching A. For 4, 2, 4 is an E, 2 is also an E, so we can just move 2 pointer forwards. We go to 5, 3. How many matching characters do we have? 2. So we can see that among all of these results, among all of the red boxes that I have here, 3 is the largest value, right? And because 3 is the largest value, we're going to return 3. So this is the brute force recursion solution. And what is the runtime complexity of this? So you can see that the height of the tree is equal to m plus n, where m is the size of the first string, and n is the size of the second string. And at each level, we have at most 2 decisions to make. So that means the total runtime complexity is going to be O of 2 to the power of m plus n. The question is, can we do better than this? The answer is yes, we can do better with this problem by using dynamic programming. And why do I think about dynamic programming? So you can see that each of these is actually a sub-problems, right? So what does this subproblem tell us? It tells us that if we start at index 2 of the first string and index 1 of the second string, what is the longest common subsequence that we can create? And these subproblems actually repeat themselves, right? You can see that these subproblems here and these subproblems here are exactly the same. So we start at 3, 2. So whenever we see repeated subproblems in a decision tree, we always think about dynamic programming. So that's the core idea of dynamic programming. We have the big problem, and we want to break it down to smaller problems, and we only compute each sub-problems exactly once. So that's the core idea of this. Dynamic programming has two approaches, the top-down approach and the bottom-up approach. I always prefer to use the top-down approach because it's very similar to the brute force solution. It's very intuitive and easy to understand. So in memorization, what do? We're gonna catch the sub-problem inside data structures. So usually I will use a hash map. So what do we store in a hash map? We're going to store the sub-problem as the key. So our sub-problem here is going to be index I and j, right? I represent the index of the first string and j represent the index of the second string. And the value is going to be the longest common subsequence that we can create from the substring of text 1 starting at index I and the substring of text 2 starting at index j. So this is the subproblem we're going to store in the hash map. And I represent the hash map here as a 2D matrix because it's easier to visualize this as a 2D array rather than a hash map. All right, so we're going to start at 0, 0, right? We're going to start at the beginning of both strings. That represent this position. And this is the position we try to look for the answer, right? So if we figure out the answer in this position, we will return it immediately. So we see that as 0 for text 1 is an A, 0 for text 2 is also an A. So we can create a match between them. So we're going to move to 1, 1. Do we have the answer for 1, 1? No, we don't have the answer for 1, 1. So we have to compute it. B doesn't match a C, right? So we have two options. We can either move to 2, 1 or we can move to 1, 2. Do we have the answer for 2, 1? No, so we continue. So 2 for text 1 is a C, 1 for text 2 is a C, so we see a match, right? So we're going to move to 3, 2. 3 for the first string is a D, 2 for the second string is an E, so we see a mismatch. So we're going to go to 4, 2 or 3, 3. So let's start with 3, 3 first. So 3 for the first string is the D and 3 for the second string is the end of the string. So whenever we reach the end of one of the strings, we're going to return, right? Because we cannot continue this path. So what should we return here? If we have no more characters from the second string and we have 2 characters left for the first string, what is the longest common subsequence we can create? That subsequence we have a sign of 0, right? So that means 3, 3 should return 0. Or the position ending at 3 should return 0 as well. So 0, 0, 0, 0, 0. And the same for the first string, right? So all of the position ending at 5 should be 0 as well. Alright, so now for 4, 2. 4 for the first string is an E. 4 for the second string is also an E. So we have a match, right? We're going to move 2 pointers forward. We move to 5, 3. 5, 3, we look into the table. We see that it's a 0, right? And because 5, 3 is 0, that means what is the answer for 4, 2? 4, 2 is going to be 1. Why? Because we found a match at index 4 and at index 2 of both strings. And what is the answer for 3, 2 then? So 3, 2 have 2 options, go to 4, 2 or 3, 3, right? So that means we should take the max between these two, right? Because we want to find the longest common subsequence. So 3, 2 is going to be 1. And what is the answer for 2, 1? So 2, 1, we found a match, right? So that means the answer for 2, 1 should be 1 plus 1 or 2. So 2, 1 is going to be 2. So now we're going to start with this branch, 1, 2. Do we have the answer for 1, 2? No. So we continue. So 1 for the first string is a B. 2 for the second string is an E. So we have 2 options, right? We can move to 1, 3 or we can move to 2, 2. So we see that 1, 3 in the table, we already have it, 0, right? So we're going to return 0. For 2, 2. So 2 for the first string is a C. 2 for the second string is an E, so we see another mismatch. We have 2 options. We can go to 2, 3, or we can go to 3, 2. Alright, so this is where things get interesting. We see that 3, 2 in the table is a 1, right? That means we already computed these subproblems before. And if we already have the answer, we can just get this information from the table, right? So we're going to return 1 immediately. For 2, 3, we already reached the end of the second string, so we return 0. This is why dynamic programming is so powerful, because it allows you to compute the subproblem only once. Now, what is the answer for 2, 2? It's going to be the max between 1 and 0, right? So 2, 2 is going to be 1. What is the answer for 1, 2? It's going to be the max between 1 and 0. So 1, 2 is going to be 1 as well. What is the answer for 1, 1? It's going to be the max between 2 and 1. So 2. And what is the answer for 0, 0? At 0, 0, we found 1 matching characters, right? That means the answer for 0, 0 is going to be 1 plus 2. So it's going to be 3. Once we figure out the answer for 0, 0, we know this is going to be the answer we're going to return. So we're going to return 3. So what is the runtime complexity of this solution? So you can see that how many subproblems do we have here? We have m times n subproblems, right? Where m is a sign of the first string and n is a sign of the second string. For each subproblem, we only compute it exactly once, right? And how much time we need to compute each subproblem. So at each subproblem ij, we only have 2 options, right? At most 2 options. So either go to I plus 1j or go to ij plus 1 if there is a mismatch. And if there is a match, we're going to go straight to I plus 1 and j plus 1, right? So that means the total runtime to compute each subproblem is a constant time operation. So the runtime is going to be O of m times n. How about the space complexity? So the first space we use is going to be this hash map, right? So the size of the hash map is what? M times n. And the second space we use comes from recursion. So because I'm using a top-down approach, I have to implement it using recursion. And that means there are going to be some extra space that goes into the call stack. So what is the maximum number of functions called in the call stack? Remember, when I draw the decision tree, the height of the tree is m plus n, right? That's going to be the maximum number of functions called in our call stack, m plus n. M plus n is significantly smaller than m times n. That means the total space complexity is going to be O of m times n. Let's code this up. First, I will define the hash map. I call that memo. It's going to be an empty hash map. Then I will define a helper function. So I will call that function DFS because we are using backtracking DFS in this case. And I will take in ij. So I is the index of the first string and j is the index of the second string. So what is the base case? The base case is whenever we reach the end of either one of the string, right? So if I is equal to the size of text 1 or j is equal to the size of text 2, we're going to return 0 because that's the longest common subsequence. The second base case is if ij is already in memo. That means we already computed subproblems. We're going to return it, memo ij. If this is not the case, we have to compute the answer for ij. So we have two options. If text 1 I is equal to text 2 j, we're going to recursively call the problem for I plus 1 and j plus 1, right? We also need to add 1 at the end because now we found one matching character. That means our longest common subsequence we increase by 1. And we're going to assign that to memo of ij. Otherwise, we're going to assign memo of ij equal to. So whenever we see a mismatch, there are two options, right? We can either increment I forward or increment j forward. So if we increment I forward, the result is going to be DFS I plus 1j. If we increment j forward, the result is going to be I j plus 1. And we want to take the maximum between these two values. At the end, we're going to return the result of the subproblem, memo ij. So after I define this function, I will call it in the main function. So we're going to return DFS 0, 0, because when we first start, we start the beginning of both strings. So let's run this. So it passed all the test case. Let's submit. So as you can see, the solution passed and it's pretty efficient. So that's it for this video. I hope you enjoy it. If you like the video, please like and subscribe. That supports the channel a lot, and I will see you in the next video. Peace.